So when there's a closed loop of wire in an external magnetic field with a current around it, right, with a current through the wire, there's an interesting thought experiment that can be done. If this loop is allowed to rotate freely over time, does it continue for infinity, or does it eventually come to a stop, and if so, where? Feel free to pause the video now, consider it, think about it, right? I will, for the rest of this video, show you the actual answer, right? So feel free to pause now, think about it, and then unpause when you're ready to see how it works. All right, so this is the picture that you should recognize from the previous video, okay? We have several things here. We have the area vector, right, perpendicular to the face, AB. We have loop or segment 2 here coming out of the screen or the page towards us. The X means that current in segment 4 is going into the page, okay? So there are two forces, up and down. The external magnetic field is not moving in space, right? That's always pointing to the right, okay? So that creates a torque on it, remember? Torque, we found, was I times A, that area vector, cross B, okay? What I didn't mention last video was that this value of I times A is known as the magnetic moment, right? The magnetic dipole moment. And it's kind of a dipole because, well, you only have two current directions, two segments of this closed loop acting kind of like a dipole, kind of. And so this is mu. And so you can also write the torque as mu vector cross B. Okay, so keep that in mind. All right, so now let's let this loop, or let this segment, continue to rotate. What would happen? Well, let's see here. Let me... that. We have... let's do it this way. Let's rotate it such that that angle becomes 0, right? The angle in between A and B becomes 0. What I mean is that the rod is basically up and down, okay? And so we have, this is segment 2, which was into the page, or sorry, out of the page. I always get those mixed up. I'm sorry. The X is into the page, and that's segment 4. In green, magnetic field still to the right. Okay. And let's do the right-hand rule again. So the magnetic force, remember, is IL cross B. So point your finger in the direction of L for segment 2. That's into and out of the page, right? Perpendicular to the screen. And so in that segment 2, the current is coming out of the page. So pointing finger up. Middle finger in the direction of B, so to the right. That means our thumb should point directly up. So I'll keep consistent with the picture and just write that as F2. On the bottom, it's kind of the opposite, right? Your index finger into the screen, into the page. Middle finger in the direction of B to the right means that your thumb points downwards. So F4, okay? And those two forces are equal and opposite because this is a steady current and a constant, a steady magnetic field. So those equal and opposite, thus this rod doesn't move anymore, right? There is effectively 0 torque. Why? And what I haven't drawn is the area vector A, right? A, IA cross B. If we evaluate this, the angle in between A and B is 0. So IAB sine of 0 gives us 0 torque. And so this on the right here is a state of minimum potential energy. there is zero torque on it, and thus it will not want to continue rotating. It will remain stationary like this for the rest of time until or unless some outside force comes in and pushes it, right? Say we come in with our finger and nudge this rod some angle that way, right? Right? And then we release it. In that case, we have the following. Eraser, there we go. In that case, we have the following. So let me do that again. I'm kind of going to draw it a little bit smaller maybe. Now we have some kind of rod like that. Still our axis, magnetic field. Still horizontally to the right. Our area vector now is pointing at some angle, but now it's pointing below the magnetic field direction. Okay, and see, this was section 2. The directions for the currents haven't changed. So now, which direction is the force? Well, right-hand rule, out of the page for 2, middle finger in the direction of B, there's still a force upwards. Same thing for down on 4, even though I don't have room. F4. So the forces haven't changed direction. Okay? So that means that now this will rotate back towards the equilibrium. It'll rotate back to what we had over here. Okay? In fact, once you release the rod, say from this orientation, it will rotate towards equilibrium, but because it has some rotational inertia, it'll actually go a little bit past equilibrium till it comes to a stop, and then it'll rotate back, and we'll probably pass it again, but rotate back a little bit further. And every time this, we'll say, amplitude gets smaller and smaller until after an infinite time, we come to rest exactly at its equilibrium position with zero torque. So in the future, in your transfer courses, you may have to calculate that, say, that angular frequency with which a rod oscillates, right? But we won't do that here. But just know that that's what would happen. And so in order to have that not happen, engineers have gotten very clever. Can you guess what they've done in order to not have the rod oscillate back and then just remain at the equilibrium position? Pause the video, try and guess what you think they may do to not have this occur. So it turns out that in order to have a rod, right, or a current loop that's subjected to an external magnetic field, it'll be rotating. In order to have it not come to a stop, they flip the direction of the current in the loop. That's the trick. If they flip the direction, let's reanalyze. Whoa, that's a big eraser, sorry. Let's reanalyze. So this, instead of coming out of the page, would go in. Conversely for the bottom. So now this loop would go in. That's still that's still F2, or that's still 2, side 2, and this is coming now out. And that is still 4. So evaluating the right-hand rule again, let's see, on segment 2, right, up here, that pointer finger now is going into the board, middle finger in the direction of B to the right, now means there's a magnetic force downwards. I'll draw that just to the side. There's a B2 downwards now. Okay? Conversely, for point 4, there's a force upwards. They're flipped from when the directions of the current were flipped. And that is very important because the fact that when this is rotating, it passes equilibrium and comes to a stop over here, like what I have down below, what I actually should write is I actually should do it down here, because we'll be able to see that the direction of rotation will continue. So that's a cross, whoops, that's a dot. So now that's segment 2 and that's 4, like before. So now we have a net force downwards, net force upwards, right, on those respective halves of this loop. And what does that mean? Happens to the rotation of the loop? Well, it continues to rotate. If the forces are on this segment 2, if they're down, and on segment 4 up, well, that's going to make this loop approach, quote unquote, horizontal, right? And so eventually it'll go to that orientation, then this orientation, then this orientation, and this one again, and we do the exact same thing. They flip the direction of current again, and then it continues around. So every time you have a maximum torque for this closed current loop, the current direction flips, right? Excuse me. And that's the crux of an electric motor, right? You have some mechanical object, in this case a closed current loop, physically rotating, right? Mechanically in motion. And it's using that mechanical motion to generate electricity, right? It's hooked up to a means to generate electricity, right? So actually it's a generator. I'm sorry, it's an electric generator. Right? Actually, no, it's a motor. Let me write this down. So this is the crux behind, and you can call it an electric motor or just a motor in general. It's the basis for a motor, right? A motor utilizes mechanical energy, and we have that from the rotation of this physical loop, right? And that generates electrical energy that other systems will use, okay? So this is very, very handy in the case of engineering and engineering applications for everyday life. Can you think of any examples? Thanks for watching.